Welcome to a cosmic edition of Programming Problems, where we will be expanding our mind on day 11 of Advent of Code 2023. In our quest, we encounter an elf who is a researcher, and we are asked to help with his observation analysis. The data that we are requested to analyze is a single giant 2D image containing empty space and galaxies. The empty space is indicated with dots, while the galaxies are visualized as hashes. For the problem, then, the elf is interested in the distances between the galaxies, but there is a catch. Rows and columns without any galaxies are twice as big after the universe expands, which it does. After the expansion, what is the sum of the lengths of all the shortest paths between every pair of galaxies? Here is the example shown in the problem description. Note that on the left side, we have our universe before expansion, and on the right, we have the universe after expansion. Do you see how every row and column without galaxies is inflated to double the size? Now, suppose that we have our expanded universe. Then we're left with the task of determining the distance between every pair of galaxies. In this case, I've shown two pairs. The pair on the left has a distance of 9, the pair on the right, a distance of 6. And that's it for the problem description and examples. Let's see how we can tackle today's problem as we jump into the solution. While we could expand the grid into a new, larger grid, this seems like asking for trouble. Plus, because the distance calculation is straightforward if we have the coordinates of galaxies after the expansion, then let's see if we can do without making larger grids. And of course, this is something that is possible. We can compress the expansion by iterating over the grid's rows and columns and then tracking the expansion thus far. For example, at the top of the grid, we start counting with 0. Then, as we iterate over the columns, we find that every empty column will generate one additional column worth of empty space. So any and all columns after this first empty column will need to have one additional unit of space added to their horizontal location. As we encounter the second empty column, we again have one more unit of space that needs to be added, and so on. The same then holds for the rows. So, if we construct these two lists of offsets, then based on the original position of any given galaxy, we can simply find the offsets to its position in constant time. The solution outline then looks as follows. We collect the offsets and then collect all the real positions of the galaxies. Once we have the galaxies, we can do an order n² comparison to compute all distances. Note that for convenience, the rows in the grid here are split into a list of characters, as opposed to strings. This makes manipulating the grid somewhat easier for today's problem. Getting the row offsets is simply done by looping over the grid row per row. We initialize the list of offsets with an initial 0 to bootstrap the sequence, but we'll remove it when we return the offsets at the end. Then for every row, we assume that it's going to be empty. If we find a hash in any of the columns, then it is, of course, not empty, so we break the loop. After checking the columns, we act based on whether the row was empty or not. If it was empty, then we need to add an additional unit of space to the list of offsets. So we take the last known offset from the end of the list, and we add 1. If it was not empty, then we just take the previous offset and add it again. Getting the offsets for the columns is trivial if we manage to rotate our grid 90 degrees counterclockwise. Here's a short way to do this in Python. Once the grid is rotated, then the columns have become the rows, so we just apply the previous function. At this point, the universe is expanded, so we just have to collect all galaxy positions. Here we loop over the grid as per usual, and then we take the row and column offsets from the lists which we computed before. The actual position, then, is the current position plus the offsets, which we append to our positions list. Finally, computing the total distance is done by iterating using two indices, I and II. By always iterating II from the point of I plus 1, we ensure that we don't take duplicates. The distance itself is simply the Manhattan distance, or just the absolute difference in x plus the absolute difference in y. And that was it for part 1. On to part 2. Turns out that the galaxies are much, much older and farther apart than the ELF initially estimated. So instead of expanding every empty row and column to be twice as big, they are now 1 million times as large. After the expansion, what is the sum of the lengths of the shortest paths between every pair of galaxies this time? Because the problem is so similar, let's go straight to the solution. Ready? Let's go! Turns out it was a good idea to not recreate the grid. Who could have predicted that? Instead, we'll apply the same trick as for part 1. However, in part 1, we expanded empty lines with one additional empty unit of space. Now, if we were to turn one space into 10 units of space, this would mean that we have 9 additional spaces. This then also means that if we were to replace one row or column with 1,000,000 rows or columns, then we need to add 999,999 additional units of space. The example shows how the row offsets look if space were to expand to 10 times as large. The change in code then is very minimal. Instead of adding one additional unit of offset for every empty line, we instead add 1,000,000 minus 1 units. And that's it for the problem of today. You now have 2 more stars within your reach. Thank you once more, and let's see what tomorrow brings.